Today we're going to learn the process for taking derivatives implicitly, among a few other things. Now, before we get started, I think it's important to talk quickly about the meaning of the words implicit versus explicit in the English language, because there are some parallels here. So, if you walk into a restaurant, you will probably see on the door things that say, no shoes, no shirt, no service. And you also might see a sign that says no soliciting. Okay, those would be explicit rules for the restaurant. Okay, they are directly stated. There are also many implicit rules for the restaurant. For example, it probably would not be a good idea if you walked into the restaurant, walked into the kitchen, and started throwing dishes around. Okay, but that rule is not directly stated anywhere. So implicit rules are rules that are implied. They're understood based on rules of society, or maybe even the laws of the city you're in, but they're just not written down anywhere. In mathematics, you have equations that are defined explicitly, which means they are y equals functions of x. In other words, the y is only on the left side. But then there also are functions or relations that are defined implicitly, which means that you might have multiple y's on the same side and still need to find the derivative. Okay, with this process we're going to learn today, that's possible, even if you can't solve this explicitly for y. Now, today it's very important that we remember, understand, and believe in the chain rule that we learned last class. Okay, the chain rule is vital for today. We have to believe that it does what it says it does, even though we may not be able to confirm that by hand. Okay, so believe in the chain rule as we go throughout today's exercises. All right, let's take a look at this. The derivative of the quantity f of x squared, what would this be? Okay, this is something kind of new. Well, on the outside, this is a object to the second power, so the power rule applies here. So the power rule says bring down the 2, leave the inside alone, change the exponent to a 1, but then the chain rule says I need to multiply by the derivative of the inner function. In this case, the inner function is just f of x. We don't know the formula for f of x, it's just a symbol, okay? But the good news is we have a symbol that stands for the derivative of f of x. We have several, actually, and the one that probably makes most sense in this situation is just to use the symbol f prime of x. We could also use dy dx. We could also use y primed and a couple others. So as far as symbols go, that's how you take the derivative of something that looks like quantity f of x squared. We apply all the rules that we know, and we believe in the chain rule, which means we multiply by the derivative of the inner function. So that should make sense to you, and I think if that makes sense to you, then it should not be a big mystery how we would take the derivative of y squared. Okay, first of all, we need to understand y here is not a variable. Y is a implicit function. I don't know what y is equal to, just like up here I did not know what f of x was equal to, but that's okay. I'm just going to treat it as a function that's unknown. I go through my rules. Okay, my rules say if I have something squared, then the derivative of that is 2 times that function times the derivative of that function. Okay, the derivative of y. And we have many ways to write the derivative of y, and it's your choice which one you like to use. The most economical as far as writing goes is just to write y primed. So the derivative of y squared is not just 2y, because we believe in the chain rule and we understand that the variable here is implied to be x, not y. Y is a function. Okay, so the technique is called implicit differentiation. Implicit we already talked about, and then differentiation is the process of taking a derivative. Here's how it works. We have an equation that has x's and y's in it, and we're going to take the derivative of both sides of the equation with respect to x. So we understand x is the variable, y is a function. It's important to believe in the chain rule in this process. Once the derivative is taken, some algebra is required, and we need to solve for the derivative of y, if that's possible. There'll be times when that might not be possible. Okay, so here's a relation, x squared plus xy plus y squared equals 27. I cannot solve this for y explicitly. Can't be done. So I need to use implicit differentiation. So we take the derivative of both sides. Let me write out that process, and then we'll get to work. The derivative of x squared plus xy plus y squared. And on the right side, I have the derivative of 27. We used to play a game when we did this face-to-face where I would do the right side and you would do the left side, okay? Because it's very easy for me to do the right side. The derivative constant is 0. Now, the derivative of a sum is the sum of the derivatives. So I have the derivative of x squared, which is 2x. We've already done the derivative of y squared on the previous slide. That's 2y times y primed or times dy dx, whichever symbol you like to use. And now I need to do the derivative of xy. Okay, so I'll put a plus sign here. Now, I'm going to go off to the side here. What is the derivative of xy? In other words, the derivative of x times y. Okay, that's telling me the product rule is in effect. So let's label our pieces here. U is x. U primed is 1. V is going to be y, and the important thing here is not to make the mistake of calling v primed 1, because remember, y is not the variable here, x is. So the derivative of y is called y primed. Okay, so now the product rule says v u primed, so y times 1 plus u v primed, so x times y primed. Okay, we've taken the derivative of both sides. We've done step number 1. Now my goal is to solve for the derivative of y. So I notice that there are two terms that contain y primed. I need to solve for y primed. So generally speaking, in algebra, we want to get everything that doesn't have the variable we're solving for on the other side of the equation. So I need to subtract 2x and y on the other side. So minus 2x plus 2y. That leaves me with xy primed plus 2yy primed on the left side. And now how am I going to solve for y primed? Well, I'm going to factor out the y primed from both terms, which leaves me with a x plus 2y. And then I can divide both sides by x plus 2y and I'll be finished. Now, notice here that when you do a derivative implicitly, in this case, your final answer does not just depend on x, as they have been in the past. Normally we've had a derivative, it only had x's in it, so all you had to do is plug in an x value to get a slope. Now, your derivative has x's and y's in it, which means if you want a slope at a specific point, you need the x coordinate and the y coordinate. Sometimes those are both given to you. Sometimes you need to go fishing for one or the other. Okay, and you'll see some examples of that as we go. All right, write the equation of the line tangent and the line normal at 2, 3. So they've given us the x's and the y values, that's good, of this curve, which may or may not be a function. Okay, it's a relation that involves x's and y's. So we need to take the derivative implicitly, the derivative of both sides, and then solve for y primed. So we have 2x is the derivative of x squared. We just did the derivative of xy, so I won't go through all the steps here, but it's going to be y plus x y primed, and the derivative of y squared is going to be 2y times y primed. The derivative of 1 is 0. Let's solve for y primed. So again, I'm going to subtract the two terms that don't have the y primed from both sides. I'm going to factor out the y prime from what's left. And solve for y primed if possible. In this case, it is possible. So this is now my derivative. This is my slope finder. And so if I need to find slopes, which I do to write the equation of tangent lines and normal lines, I need both x and y coordinates. Okay, so let's see. Let's go over here. let's write m tangent for the slope of the tangent line. And then let's write m norm for the equation of the normal line. Okay. The slope of the tangent line is going to be negative 2 times the x-coordinate. The x-coordinate is 2, so that's 4, plus the y-coordinate, that's 3, divided by the x-coordinate, 2, minus 2 times the y-coordinate, 6, which comes out to be negative 7 over negative 4, which is 7/4. The slope of the normal line is going to be the opposite reciprocal of that number. And now I can write the equations of the two lines. So the tangent line will be y equals 3 plus 7/4 times x minus 2. And the normal line, the line that's perpendicular to that line, at the same point, will be y equals 3 minus 4/7 times x minus 2. This is a common AP type question. It asks us to find what points on this curve is the tangent line horizontal, which means the slope of the curve is 0, and at what points on the curve is the tangent line vertical, which means that the slope of the tangent line is undefined. So to do that, we need the slope finder, which is the derivative, so I need to do the derivative implicitly. The derivative of y squared is 2y times y primed, and the right side is nice and easy because there are no y's, just x's, so I get 3x squared plus 6x, and the derivative of a constant, of course, is 0. Solving this for y primed, we get that the derivative depends on x's and y's again, so I have 3x squared plus 6x over 2y. Now, this is going to tell me slopes of the curve at various points. I'm asked to find when is this slope equal to 0. So that's equivalent to asking myself, when does 3x squared plus 6x over 2y equal 0? And I go back to my pre-cal days, and I know that a fraction is equal to 0 when the numerator is equal to 0 and the denominator is not. So when I solve for x here, I'll double check that those numbers don't make the y or the denominator equal to 0 as well. Okay, so let me write if that and 2y does not equal 0. Okay, so I need to solve this equation. 3 and x are common factors. We're left with x plus 2 equals 0. And that means that when x is 0 and when x is negative 2, my numerator is equal to 0. Okay? Now we're going to find the y values now that go with these x values to double check that that doesn't mess up the denominator. Okay, so what happens when x is 0? Well, when x is 0, you get 0 plus 0 minus 2 equals y squared. So that means y squared equals negative 2. But that's not possible with real numbers, okay? So that means we can reject x equals 0. When x is negative 2, we're going to get negative 8 plus 12, so that's what, 4, and minus 2. So we get y squared is equal to 2, which means y can be the positive or negative square roots of 2. I go back to my derivative. That's not going to make the denominator 0, so those 2 points are good. What 2 points am I talking about? X is negative 2, y can be 2 values, the square root of 2, or this negative 2 comma the negative square root of 2. So those 2 points on the curve, the tangent line is horizontal. All right, now for vertical tangents, the denominator will be 0, but not the numerator. So now I'm asking myself, when does 2y equal 0? That's going to occur if y is equal to 0. Now, what are the x values when y equals 0? I go back to the original curve, and that means I need to solve 0 equals x cubed plus 3x squared minus 2. This is not quadratic, I can't factor it by grouping, so I'm going to try some synthetic division, but I need to guess appropriately. Okay. Now the choices here are positive and negative, 1 and 2. Okay, those are the choices to test for synthetic division to see if this has any rational roots. So I can start with 1, and I can just plug in 1 because I can do that mentally. Okay, so 1 plus 3 minus 2 is 2. That's not equal to 0. So 1 is out. Now what about negative 1? Negative 1 plus 3 times negative 1 squared, that gives me positive 2 minus 2 is 0. So negative 1 works. Now I need to do synthetic division to figure out how that is going to factor. So I'll put negative 1 on the shelf. 1, 3, 0 is the coefficient of x, and negative 2. Those are the coefficients. So synthetic division says bring down the 1, multiply, add, multiply, add, multiply, add. Okay, I get a remainder of 0. That's what I expect. So what does that mean? That means that the x cubed plus 3x squared minus 2 is going to factor as x plus 1, or x minus negative 1, right, times x squared plus 2x minus 2. Okay, obviously I know that negative 1 is one of the solutions. My next question is, does this quadratic have any real solutions? And I can double check that quickly with the discriminant. B squared minus 4ac. B squared is 4. Minus 4 times 1 times negative 2 is an 8. So this has 2 more solutions that can be found with the quadratic formula. So x equals negative 1 is a solution, and also these 2 are solutions as well. Negative 2 plus or minus the square root of b squared minus 4 times a times c. So that's 4 times 1 times negative 2, which is a positive 8, all divided by 2 times a. So in this case, there were 3 points on this curve where the tangent line was vertical. Negative 1, 0, and then these 2 numbers, comma 0. Okay, now what comes up in calculus quite a bit is the need to take the derivative of the derivative. Okay, the derivative of the derivative. So we call this the second derivative, which makes sense. The first derivative is dy dx, so if we take the derivative again, we call it the second derivative. And there's really no limit to how many derivatives you can take. It's just a matter of, are they useful once you can take them. But what we want to talk about on this slide here is the notation for second derivatives. Okay, in differential notation, okay, if you just treat these as fractions, and think of them like you're multiplying, you're not really multiplying, but if you were, then this is what you would get when you multiply these things together. You would get d squared y over dx times dx is dx quantity squared, and for economical purposes we don't write the parentheses. So this is the symbol for the second derivative in differential notation, okay, which can also be rewritten as, you can guess, y double primed or f double primed of x. All 3 notations are going to be used in the course, so you need to recognize them. These are pretty obvious. This one is not so obvious. So look at this one a little bit and just understand what it looks like. Okay, I took the derivative 2 times of y with respect to x twice. That's what it means. All right, let's do one example with the second derivative. Find the second derivative for this curve, and in the end you only have x's and y's, not any y primes. Okay, you'll see what I mean here. So let's do the derivative implicitly. We get 6x squared minus 6y, y primed, equals 0. We go through our normal steps and we want to solve this for y primed if possible. Okay, I'm going to move the 6y, y primed term to the right side so that they're both positive. Now, 6's cancel, and I'm going to get x squared over y equals y primed. So what do I do next? Well, to get y double primed, I'm going to take the derivative of both sides. Okay, simple enough on the right side. I just write y double primed. Not so simple on the left side, because now I have a quotient rule. I have a quotient. I have x squared divided by y. So I'm going to do u equals x squared, and your y is equal to v. So that means v primed is equal to y prime, right? Not y, not 1. And your u primed is equal to 2x. Okay, using that I can use the quotient rule, which says v u primed, y times 2x, minus u times v primed, so that's x squared times y primed, all over v squared. And what's v? V is y, so y squared. Now, this is almost good, but I don't want to have a y primed in my answer. And since I've already solved for y primed up here, I can replace it. So my answer in terms of only x's and y's is going to be, if I clean this up a little bit, 2xy minus x squared times y primed. Okay, and y primed is x squared over y, so I'm going to get x to the 4th over y, all over y squared. That could be simplified a little bit so that there's no compound fractions. And if you're doing a multiple choice question, you'd need to, but for our purposes, that is an acceptable answer.